Two identical point charges, each of charge plus q, are fixed at two vertices of an equilateral triangle of side length a. Assume the charges are stationary in a vacuum and let k denote Coulomb's constant. Derive an expression for the magnitude and direction of the net electric field at the third vertex in terms of q, a, and k. So here I've drawn sort of what the setup should look like. So each of these lengths is the length a, and we have two identical charges at two of the vertices, and we want to find the electric field here. And I've labeled each of these charges either 1 or 2. And so remember that the electric field's direction is always either radially outward or inward from a point charge. And it would be pointing radially outward if the point charge is positive, and inward if it's negative. So based on that information, we can draw the electric field from each of these point charges at this point here. So at this point, we will have an electric field going this way from point charge 1. And we will also have an electric field going this way. And so we'll be pointing this way, and this is E2. And we want to find the net electric field. So remember, electric field can just be found using superposition. So the net electric field is just the sum of all of the individual electric fields. And electric fields are vectors, so we have to be careful to sum their components. So for example, let's choose this direction to be the positive x direction, and this direction is the positive y direction, and is our unit vectors. I hat is a unit vector in the x direction, and j hat is a unit vector in the positive y direction. So now that we have this, let's decompose each of these vectors into their components so that we can actually add their components to find the components of the net electric field vector. So this is E1y, this is E1x, and then it will be similar for the other side as well. So this will be labeled A2y, E2y, and I'm not going to explicitly label it just to save space. So let's start with the x components. And to do that, we just sum each of the individual x components. And note that they're pointing in opposite directions, so one of them will be positive. So the electric field resulting from point charge 1 will be positive, and the electric field resulting from point charge 2 will be negative. And it turns out that these two are actually equal. The magnitudes will be equal. So to be more explicit about y is equal, let's do some trigonometry. So let's call this angle theta. And since this is an equilateral triangle, all of these angles will be theta. And then from that, we get that this angle will also be theta. And we can use that to figure out what all of these electric field components are. And this angle here is also theta. And this is just from geometry. And so from that, we can decompose each electric field vector. So E1x will then be E1 times the cosine of theta. And know that theta is equal to 60 degrees because it's an equilateral triangle. And E2x is E2. It's equal to E2 cosine of theta. And first let's derive what E1 and E2 are. So this represents the total magnitude of E1, And this is the total magnitude of E2 here. And so we get that E1 is equal to kq over a squared. This is just the formula for the magnitude of the electric field at some distance a from some source charge q. And note that this is also equal to the electric field of this charge here, since they're both equidistant and have the same charge. So that means that E1x is equal to E2x, since these two are the same. So if I erase the subscript, and they are both multiplied by cosine of the same angle. So these two are equal, and this becomes 0. So the electric field in the x direction will be 0. Now let's do something similar for the electric field in the y direction. And this time, notice how both y components are actually positive. They're both in the positive y direction. So we will have that the total y component of the net electric field is just the sum of the y components of the individual electric fields. And again, we can compute each individual electric field using trigonometry. And so this is going to be E1 times the sine of theta, because sine of theta is E1y over E1. So E1y is E1 times sine of theta. And it's the same thing for E2, since this angle is also theta. And we know that E1 equals E2. So I'm just going to drop the subscripts here. So now if we add them, that means that the net y component will be 2e sine theta. And now let's plug in our values. So e is kq over a squared. That's what we derived here. And the angle theta is always 60 degrees. And sine of 60 is just square root 3 over 2. And the 2's cancel. So the final y component is kq times the square root of 3 over a squared. And that's our y component. So if I rewrite this up here, just erase all of this right here. Then EY is kq square root 3 for a squared. And it's in the positive y direction. So it will be pointing in the j hat direction. And so from that, we can figure out that the magnitude of the net electric field is the square root of ex squared plus ey squared. And this is just the Pythagorean theorem. So ex is 0 and ey is, so this cancels out. And this just becomes square root of ey squared, which is just ey. So the magnitude is kq times the square root of 3 over a squared. And the direction of the net electric field is upwards, in this case, in the j hat direction, or the positive y direction. And that is how you would solve this problem here.